If you want to open a brand new luxury car dealership, you need buyers with high disposable income. Your first step as an analyst is to determine the local wealth of the target location. Let's say you survey 6 local residents to get a read on the town's financial health. This dot plot shows the results. You calculate the mathematical average, the mean, by adding all the incomes and dividing by 6. The result is exactly $6,250. Based on this number, the typical income is too low to support luxury sales, so you decide to abandon the project. But then, a multi-billionaire moves to town, bringing an income of $10 million. Recalculating the average, the mean violently snaps to $1.43 million. That single massive data point mathematically drags the average upward, leaving the original 6 residents far behind. This exposes the core vulnerability of basic descriptive statistics. They are highly sensitive to extreme values. Making million-dollar corporate decisions based on naive aggregation leads to systemic failure. To protect your analysis, you need a mathematical defense mechanism against these anomalies. We can see this vulnerability in a real-world 30-day operational dataset comparing the daily sales quantities of Nike versus Adidas. Looking at the initial aggregated sums for the month, Adidas reports 1,044 total units sold, while Nike reports only 590. A surface-level reading of this initial data strongly suggests that Adidas is vastly outperforming Nike in the market. This line chart tracks 30 days of sales. On day 23, Adidas recorded a massive, unnatural spike of 689 units sold. This is the illusion of total sales. Remove that single anomaly, and Adidas actually sold fewer shoes overall than Nike. To defend against this, analysts use the median as their first line of defense. By finding the exact middle point of the sorted dataset, the median ignores the extremes to find the true center of normal operations. True operational performance is only visible when you stop looking at gross totals and begin interrogating the actual shape of the data's distribution. Finding the median gives us the center, but to understand the entire spread of a dataset, we use percentiles. We start by sorting the data in ascending order. Here are 9 student exam scores lined up from lowest to highest. Then we place 3 structural markers to divide them: Q1 at the 25th percentile, Q2, the median, at the 50th, and Q3 at the 75th. The simplest way to measure the spread is the absolute range, subtracting the minimum from the maximum. But just like the mean, the absolute range is fatally vulnerable to a single extreme outlier. The mathematical antidote is the Interquartile Range, or IQR. The IQR achieves robustness by intentionally amputating the bottom 25% and the top 25% of the data. By subtracting Q1 from Q3, we isolate the exact spread of the middle pack. For these exam scores, the IQR reveals a tight 21-point spread. The IQR successfully isolates the true normal of a dataset. Even if a glitch records a student score of 1,000%, the IQR remains unchanged, rendering random extreme anomalies mathematically invisible. We can translate the math of the IQR directly into a geometric visual known as the box and whisker plot. This diagram shows the middle 50% of our data points morphing into a central box. It starts exactly at Q1, ends at Q3, and is split by a line representing the median. To define an anomaly, we use Tukey's fences, multiplying the IQR by 1.5. We subtract this from Q1 and add it to Q3 to set absolute limits. The whiskers extend to these fences. Any point beyond them is an outlier. In practice, analysts don't calculate this manually. Python executes this geometry instantly, using the quantile function to locate boundaries and Boolean logic to filter data. When we apply this code to a regional European sales dataset, the program searches for hidden errors outside our mathematical fences. The algorithm isolates the specific $23,000 sales spike recorded in October 2022. Once detected, you have to treat the outlier. Depending on the business context, you can either execute a total deletion of the row or impute the value by replacing the extreme spike with the median. Standardizing outlier detection through Tukey's fences turns a subjective judgment into a programmable geometry, enabling automated cleaning for even the largest data pipelines. The IQR is excellent for hiding from outliers, but sometimes you need to measure the total system volatility using every single data point. Consider an economic scenario comparing the per capita income of two hypothetical countries, Uganda and France. This chart plots the wealth distribution of both nations. Both countries share the exact same mean income of $62,000, despite vastly different economic realities. To capture this difference in spread, we calculate variance. We measure the distance of every single point from the mean and then square those distances so the negative and positive values don't cancel each other out. Because variance leaves us with squared units, we take the square root of that number to get the standard deviation. This returns the metric to comprehensible, real-world units. When applied to real stock market returns, the standard deviation is illuminating. NVIDIA shows a massive spread of nearly 60%, while Reliance maintains a tight, predictable spread of roughly 25%. While both stocks may share an average return, NVIDIA's 60% spread represents a much wider range of possible outcomes, illustrating why analysts use standard deviation as a primary proxy for investment risk. So far, we have only analyzed univariate spread, looking at a single variable in isolation. We now shift to bivariate interaction to analyze how two completely different variables move together. We measure this relationship using the Pearson correlation coefficient, which operates on a strict mathematical scale running from -1.0 to +1.0. If we analyze a dataset comparing commute times against an employee happiness index, the math returns a strong correlation of -0.976. This scatter plot maps the relationship. The negative correlation means the variables act like a seesaw. As the commute time rises, employee happiness predictably and sharply falls. This predictable opposite reaction is actively weaponized as a financial hedging strategy. Investors balance assets with a negative correlation, like stocks and gold, to protect their portfolios from a total loss during a market crash. Mathematical alignment serves as a powerful predictive engine, but it remains a description of how two variables move, distinct from the mechanical causation required to prove why they do.